The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
We have Mike. So the feasibility of reclaimed asphalt pavement as aggregate and concrete pavements. And Mike is here.
Okay. So, as was mentioned, my name is Mike Berry. I'm a structures professor at Montana State University. I'm going to talk to you today about a project funded by the Montana Department of Transportation to evaluate the feasibility of reclaimed asphalt pavement as aggregate and concrete. And my colleague working on this was Jerry Stevens, who's also a structures professor at MSU. So a little outline of what I'm going to be talking about today. We're going to go over the background behind this. Very important aspect of this project is why we would do this. Go over the mix design optimization, the mechanical and durability tests that we performed on this concrete, a pilot project that we did, and then finish it up with some conclusions. So to start things off with the background, this is actually, as I mentioned a second ago, this is a very important part of this project is why would we do it, right? You might be questioning that right now. Why would you take reclaimed asphalt pavement, millings is what we're talking about, millings off of an asphalt highway and put it into concrete to use it as a pavement? And that's a very good question. That's a legitimate question. One of the reasons why, and I think that Montana has a reason for doing so, a pretty good reason for doing so. There are large stockpiles of RAP in Montana. Why is there large stockpiles of RAP? Well, one is Montana is the 4th largest state in the country in terms of size, not population. We're sitting at just under 1 million in population, but the 4th largest state in terms of area. And that means there's a lot of roads, right? And there's a lot of maintenance on those roads, and we then accumulate a bunch of RAP. Well, it's typically used, RAP gets used, quite often as aggregate replacement in hot mix asphalt. Well, the contractors in the state of Montana do not use it extensively back into their asphalt pavement. And in parallel to this project, MDT is trying to encourage and come up with a means of incentive for contractors to start using it more in their hot mix asphalt. But in the meantime, they came up with another need for it, and that's using it in concrete pavements. The other thing is we have reduced aggregate supplies in the state of Montana. In the western part of the state, where most of our population is, near the mountains, we're okay with aggregates. You go into the eastern part of the state, there's not very many people, not many aggregate or rock quarries and stuff like that for producing aggregates. And so that's somewhat of a shortfall. And then the primary reason for trying to come up with using reclaimed asphalt pavement in concrete pavements is the Bakken oil boom. And if you're from that the general vicinity of North Dakota and Montana, you can't go a day without hearing about the Bakken oil boom and its impact on the economy and the infrastructure around there. Well, this Bakken oil boom, with development of fracking and whatnot, there's been a huge boom in eastern Montana and western North Dakota, and this is brought along with it heavy truck traffic that is destroying their asphalt pavements. And MDT would like to add a concrete pavement because it's more durable and they believe that this will withstand the heavy truck traffic better. Okay? And so behind I guess the theory that they want to do, they want to come through and they want to mill the top off of their asphalt highways, then process that RAP minimally, and then put it back down in a white topping, like a 2 or 3 inch topping slab on top of what they had just milled off, and they want this to be more durable. Okay, so that's kind of the driving factors behind doing this. Other states are looking at using RAP. Illinois just finished a study to use RAP in their concrete pavements, and one of the reasons for that is they're using their fine aggregates in hot mix asphalt, but their coarse RAP they're not using everything, and so they have big, giant stockpiles of coarse wrap. So the outcomes of this research could be further reaching than just Montana. So the first thing we came up with was establishing a wrap source and coming up with a processing technique that was minimal. So all this research was conducted with wrap millings off of I-15 near Great Falls, Montana. It was minimally processed. What I mean by minimally processed, we just took the wrap millings directly out of the miller, and then we screened it on 2 different screens, a 3/4 inch screen and a number 8 screen. Everything above 3/4 that was caught on that was tossed out as waste, just big chunks of tar and whatnot. Everything that got caught on a number 8 sieve we called coarse aggregate. Everything that made it through the number 8 sieve we called fine aggregate. And we did not do any washing of the aggregates afterwards. This process yielded acceptable gradations. So this is the gradation curve of the fine aggregates. And you can see it's within the limits of the MDT specifications, or you just take my word for it. That's within the MDT specifications for fine concrete aggregate. In terms of the coarse aggregate, we deemed this acceptable. It's off on a couple of sizes, but not too bad, especially considering where we got it, right? Just milled it up off the surface, split it on number 8, and called it good, right? And so that was our minimally processing that we did. Another important aspect, it yielded about twice as much coarse as fines doing this. So we had, by weight, about twice as much coarse aggregate as fine aggregate. And then this was consistent between wrap sources. So we tried a bunch of different wrap sources from around the state and determined, and these gradation curves were about the same when we applied this process. So that was our wrap source. We did find some issues with it, okay? When we tried to quantify the moisture content, that was very difficult, right? All of this stuff has like an asphalt coating on it, and so how you define what SSD is and what the moisture content is, and how do you heat it up to burn off like the or to dry it out so you can measure these things, it was really difficult, right? And so we decided that this is going to be an issue when we go on from here. The other issue was these conglomerations of binder and fine aggregate. And so here's some pictures of some cores that we took afterwards, and you can see that both of these things would be considered a coarse aggregate, right, right around a 3/4 of an inch, but you can see that it's not really a coarse aggregate. It's really a clump of tar with some fine aggregates inside of it. And then we believe this played into our decrease in performance, which we're going to get into in a little bit, having these conglomerations in here. But we wanted to stick with our minimally processing technique. All right. So in terms of, once we had the wrap source, in terms of the mix design optimization, well, how do we come up with mix designs to meet our objectives? Our objectives were we wanted to use 15% fly ash replacement. We wanted this to help control ASR, and this to help with just on the green side of things. We just wanted to replace some of the Portland cement. So we had that fixed parameter, 15% fly ash replacement. We also wanted to maximize the wrap content. Previous research and some of our screening batches told us that you can't replace all the aggregates in concrete, right? If you replace all the aggregates with wrap in concrete, then you don't get a very strong concrete, and you can't meet some specifications. So we had to we just looked at, we had to replace just some of the virgin aggregates with this wrap, but we wanted to use as much wrap as possible. And then we also wanted to meet the minimum MDT pavement specifications, which are, it's a pretty stiff mix of 1.5 inch slump because they use a slip form paver for casting these concrete pavements. So 1.5 inch slump, 5 to 7% air, minimum 7-day strength of 2,000 psi, minimum 28-day strength of 3,000 psi, and rupture strength of 500 psi. So those are our constraints in our mix design. We wanted to meet those things. Okay. Now, how we went about doing that, right? There's some other methods out there that you can use for mix design. We chose to do a response surface methodology. One of the reasons why it was just more scientific-y. Right? It seemed like it'd be a little more fun to do. You know, I'm a professor. I'm very theoretical by nature, and I had seen response surface methodology, often called design of experiments. It gets used. What it's used for is to determine the relationship between variables and responses. Right? The variables in this case we can think are in terms of the mix designs, or what the paste content is, what the water cement ratio is, what the wrap replacement rate. Those things are considered variables, and those have effects on responses. Response being 28-day compression strength, slump, air content, those are considered responses. And so it's a method for coming up with a relationship between those two things. And in particular, the relationship between those two things when there isn't a mechanistic relationship between it. So there isn't a direct cause and effect type of thing. It gets used routinely in industrial processes, in this case, misspelled processes. So I know that that's misspelled. Don't judge me on that. I just noticed it a second ago. So industrial processes, it gets used often in that, right? And it does not get used in concrete mixture design very often. It has been used a few times, but not too much. But what it allows you to do is for a minimal amount of trials, you maximize your output, right? You understand more of the process with a minimal amount of trials. It gives you interaction between variables, and then it works really well for optimization. So this is kind of a reason behind using this response surface methodology. If you're familiar with it, we chose a central composite design for various reasons, but that's the design that we use. So we said, hey, so we did a little research project within our research project to apply this methodology to optimize our mixes. So the way the procedure works is you go into response surface methodology and you say, hey, these are my variables and these are the ranges of my variables. And then the response surface methodology says, great, do these mixes. Okay. You then perform those mixes and then measure the responses. Once you get those responses, you then plug it back into the response surface methodology, and it fits some surfaces to it. And what this step is regression. It just fits equations to your responses and applies a bunch of statistics stuff that I don't quite understand fully at this time. But then it outpops these surfaces and confidence in those surfaces, and then you can use that for optimization. That's kind of the process used. So it was carried out in 3 phases. We ran some screening mixes to get some general idea of ranges and whatnot, of the ranges of the variables and what responses were important and what variables were important. Then we did a broad range, so we did a response surface methodology over a big, wide range of variables, and in this case, 5 variables and had 5 responses and resulted in 30 trial mixes, right? We ran through those 30 trial mixes, and we had a few issues with it. Mainly, it was just off-center a little bit. We were targeting a certain area, and we were off a little bit, and so when it came to optimization, it didn't work out the way that we wanted to, so we did a more focused analysis where we kind of narrowed our scope and redirected, and which was 3 variables and 3 responses, and that one worked out really well. Okay, and I'll talk to you a little bit more about some of those results. There's the ranges. The variables that we used in the first one was water cement ratio, paste volume, fine wrap replacement, coarse wrap replacement, and air and training admixture dosage. In the second one, we used all of those things with the exception of the fine and coarse wrap replacement. Our initial study told us something about the effect of including wrap, and then we fixed that for the second response surface analysis. All right. So the first one, as I mentioned, it was a good fit. We were off target a little bit, but some of the key findings that we had, well, it told us where to aim the second time. We were trying to use a standard moisture content correction method of mix designs, and we found out that was not working. That was adding scatter to our data, and so we basically removed that and didn't do moisture content corrections afterwards, which seems a little crazy, but it actually helped us control variability by not adjusting for water, because that was adding a bunch of variability to it. And then the biggest thing that it did is it told us the effect of including wrap. So including wrap did not affect slump or air. So it didn't affect our plastic state properties. But then it has a significant effect on strength. So this is 28-day strength on the vertical axis. On the horizontal axis is the fine wrap replacement rate, going up to about 50% wrap replacement. And then the difference between each of those lines, I know it's hard to see, but the difference between each of those lines is the coarse wrap replacement rate. Right, and so going from left to right, you see that our strength just tanks when we include fine wrap, and then it also decreases when we include coarse wrap as well. So that really quantified it. This was a surface that was fit to the data afterwards, and it showed us we quantified the effect of including wrap. Right, and with an R squared value in terms of regression of around 95%. So the model fit it really well. It was just off target. So it does bad things to your concrete. And we think that we know that the reason for doing this is that aggregate binder that's on the outside of our aggregates. And when we did our more focused response surface methodology, we fixed the wrap fractions. We fixed the wrap fractions at 100% coarse replacement and 50% fine replacement, because one of our goals from the beginning was maximize the amount of wrap that we use in our concrete. we were getting a yield ratio of around 2 to 1. If I mentioned before, about twice as much coarse as fine. And so using 100% coarse and 50% fine yielded about that 2 to 1 ratio, so we could maximize the amount of wrap. And we knew that we could meet the minimum specifications with, throwing all of the wrap into it. Okay. And so we fixed those things, and then we went on and looked for the paste content and the water cement ratio and the air dosage rate that met those specifications. So we ran this response surface methodology. Again, good fits. You can see that our observed range is about where our targets were at 1.5-inch slumps, 6% air, 3,000 PSI at 28 days. So we were in the general vicinity, so this one was going to work better. And our R-squared values, our measure of how good our equations matched the data, of 98, 80, so these are all these are good. So it was ideal for optimization. So we tried some optimization. Here's just a plot of the curves or the surfaces for each of the responses, just kind of giving an output or an idea of some of the output of running these response surface methodology. Response surface, these are the response surfaces in response surface methodology. But basically, these are equations that correlate the variables to the responses. Now, once we had these equations, then you can use this for optimization. So we came into this thing and said, all right, let's optimize this thing. Let's get the mixtures that we want. So we did one mix, and we said, hey, response surface methodology, give us something that meets all the MDT specifications. Give us something that gives 1.5-inch slump, 6% air content, and 3,000 PSI is kind of what we put on the constraints there. 1.5-inch, 6, and 3,000 PSI. We said, give us that, and it returned to us. Use a water cement ratio of 0.386, use a paste content of 0.346, and use an air dosage rate of 180.3 milliliters per pound of cement. So that's the output of our constrained problem here. So then once we got that, we came back and we performed that mix in our laboratory and measured the responses. And when we did that, we got a 1-inch slump, a 5% air, and the best for last, we predicted a 3,000 PSI concrete mix, and we got 29.49, right? And then getting a 1-inch slump when we wanted a 1.5, that is within the 95% confidence interval. So we feel like we nailed that one. 5% air was within MDT specifications and within the confidence interval, so we feel like we nailed that one. And then that one, I mean, come on, we nailed that one, right? 3,000 and 29.49, right? So we're like, all right, this is working, right? This optimization is working. So then we said, all right, let's play with this a little bit. Let's make one that, I guess one thing to note about this, 0.386 water cement and a paste volume of 0.346, this amounts to about a 7-sack mix. So if you're familiar with concrete mixes, a 7-sack mix is pretty rich, right? Actually very rich for a concrete pavement. I think they're usually on the realm of around 5.5 to 6.5 sacks of cement per yard of concrete. So this is a pretty rich mix. So we said, all right, well, we don't want to cancel out the benefit by having to add a bunch more cement to this mixture. So we said, all right, let's minimize the cement. And the way that we did that is said, let's just drop off that strength. And by minimizing the cement, what you would expect to happen is the paste volume should go down, right? Because that's where the cement is in the paste. So the paste volume went down, and then to make it workable, the water-cement ratio had to go up. Right? If you remove the flowable part of concrete, then you have to add in some more flowable stuff, and so you add more water to the mix. And so so this is what the response surface methodology gave us, and it passes my test and what it should have given us, okay? And so this one, we predicted a 1.5-inch slump. We got 0.75. So again, within the confidence interval and within MDT specifications, we got a 5.4% air, and 6% was what our target was. And instead of 2,300, we got 2,269 at our 28-day strength. Again, it was right on, right? We were pretty excited about that. We said, one more. Let's do another one. Let's just maximize the strength that we can get out of this thing. In order to maximize the strength, we put the slump at its minimum value, which is 0.75. That's the minimum value that is accepted by MDT. We said, all right, let's dump some of the air to try to increase our strength. So we targeted 5, and then our strength, we targeted 3,300. We were a little off on the slump. Not too bad. Well, right on the air, the predicted air, and then again 3,300 versus 3,279. Okay, so our strengths were right on. So this was telling us, wow, this methodology works pretty well. So that's kind of the conclusion of our little mini study in there, the application response surface methodology. It works great for concrete mix design. But it did take us a little bit of time to get there. Right? We had to do some screening mixes, and then we had to do a broader and then a more narrow scope. So we went to MDT with these results and said, hey, this is what we found. And they chose trial mix 1 that met the minimum MDT specifications. And they were okay with the 7-sack mix. Right? And we do have a current study trying to get that down by using water-reducing admixtures and stuff like that, try to make it less rich in cement. But they wanted to use the high wrap mix because, again, the goal, they wanted to use as much of this stuff as possible. Then we came up, they also said, you know, we want to meet these specifications and have a higher strength. We want around a 4,000 PSI concrete mix. And the way we came up with a mix design, based on what we learned from the first one, we knew that if we cut the wrap in half, we would get that 4,000 PSI. So we came up with 2 mixes that they wanted to further evaluate. The high wrap mix, which is just the same as trial mix 1 that just met that specifications, and then a high strength mix that used half the wrap, so 50% coarse wrap replacement and 25% fine wrap replacement. And then we carried on a full suite of mechanical and durability tests. All right, the mechanical tests that we did, compressive strength, elastic modulus, tensile strength, shrinkage, and creep, and the durability properties, alkali silica reactivity, absorption, abrasion, chloride permeability, freeze-thaw, and scaling. So we knew that including wrap decreases your compression strength, but does that necessarily mean all of the other properties are going to be bad, right? I mean, does that mean that you're going to, your abrasion or your freeze-thaw performance, and not necessarily, right? And that's kind of what we found here, is just because the strength is bad doesn't mean everything else is going to be bad, right? So we did, ran those things. Here's the mechanical, or this is the 28-day compression strength. The line on the bottom here is our high wrap mix, 100% and 50% mix. This one here is our high strength mix. Any guesses on what that big guy is up there? That's what happens if you don't include wrap. Okay, so this is pretty telling. This is the same mix, same everything. Everything's exactly the same. This is what you get without any wrap. This is what you get with 50 and 25, and this is what you get with 150. Okay, so it definitely does affect your compression strength. Does that, you know? And again, it doesn't necessarily mean our other things are going to be bad. Do you need a lot of strength in a concrete pavement? No, you don't need a 7,000. All you really need is a 3,000, right? Because pavements don't attract as much load or are not counted on to carry as much stresses as like a structural concrete. Here's the elastic modulus. Again, that's what happens if you don't include wrap. And this is when you use 100% and 50%, and that's the in-between there. And you can see that the stiffness of this thing is reduced significantly. And in terms of pavements, it's okay to have a reduced stiffness, right? Reduced stiffness attracts load, right? This more flexible pavement will transfer more of the load down to the subbase and then actually have less stresses on it. So this is actually a positive thing. And Florida DOT just completed a study on a similar project where they're using wrap, and they did a finite element analysis using this reduced stiffness and showed, you know, numerically that, hey, just because you have because you have a decreased stiffness means that you have decreased stress demand on your concrete. So this is a positive thing, the concrete being more flexible. Modulus of rupture, so the tensile strength of the concrete. You can see an effect there, which goes along. It's tied to the compression strength. So we had a decrease in compression strength. You would expect that your tensile strength would be decreased. But it does meet the specifications of 500 PSI is what MDT wants, and we easily met that 500 PSI, even in the high wrap mix. Creep isn't necessarily something that's important in concrete pavements. It is in pre-stress and things of that nature. But in terms of pavements, it's not that important. But we had a creep frame, and we tested it, right, just to help quantify some of this stuff. And you know, the high wrap creeped more than the high strength, and in terms of shrinkage, the high wrap shrunk more than the high strength mix as well, right? But it's also important to note that when we applied ASHO equations for predicting shrinkage and creep, and when we did that, it was right on with predicting these things. So that's a little side note there. Alkali silica reactivity in terms of durability. This is, you know, our data showed that it could potentially be an issue, but we found the problem to be, you know, this is filled with asphalt pavement, right? So you have a tar coating on everything. This test procedure that we used involved heating these bars up to 180 degrees, and when you heat tar up to 180 degrees, then it changes its properties and it expands. And that's what we're trying to test with ASR, is the expansion. So that was causing that was affecting our results. So this test method wasn't necessarily applicable to this material. And this was also found with an Illinois study using RAP as well, that doesn't necessarily work. In terms of the other durability properties, abrasion, it performed just as well as our control specimen. Chloride permeability, it had moderate likelihood. Freeze-thaw performance, it performed great with respect to freeze-thaw. The durability factor of 100 means it was perfect, so it was close to 100. And the scaling, moderately susceptible and slightly susceptible. So scaling was not determined to be an issue. And so in terms of durability, everything was fine. Decreased strength, we're okay because it's going to attract less load, and you don't need a lot of strength with it. Anyway, so we thought those were pretty positive results. So then MDT wanted to do a pilot project. So this is a pilot project we did outside of Lewistown, Montana. We had, up there we made 3 10-foot by 10-foot by 10-inch thick slabs. If you notice, there's more than 3 slabs here. There's a whole section of slabs. This is on an approach road that gets quite a bit of traffic in and out of a rock quarry in Lewistown, Montana. The empty spots right here is where we put our wrap pads. The rest of these things are some other recycled material concretes that we're using, involving fly ash and pulverized glass as the aggregate. So those are sitting on this test slab in Lewistown, Montana as well. There's some pictures of him casting. So we wanted to evaluate the batching and mixing process to see whether or not that works when you actually apply what we learned in our lab out in the field. It worked great. We did do slump adjusted our concrete because we could not account for the moisture content in the aggregates correctly because of the wrap. So we did apply to, or we just slump adjusted it. We targeted the 1-inch slump. We just added enough water until we got that 1.5-inch slump. The air was what it's supposed to be when we did that. The strengths were right on. And I have to, since I was boasting on my I don't have the values up here, but I was boasting on my strength values and the predictions. And on one of these test slabs in our high wrap mix, at 28 days, the concrete strength was 3,001 psi. I mean, it looks fabricated, but it was real. And that was the average of 3 test cylinders that we got that 3,001. But it was pretty interesting. So then we applied it there. Here's some pictures. Right, slump adjusted it, evaluate the field performance. They've been down for about a year, and we're just monitoring, see if there's any curling associated with it, or how it's handling the traffic and stuff. So here's just some pictures of them constructing those slabs. So in conclusion, response surface methodology was slick. Okay, we thought it was really neat to apply it here. I think back to my PhD studies when I was studying, coming up with numeric or finite element models to model reinforced concrete columns, and this would have been perfect for that, being able to minimize the amount of input I had to put and maximize my output. So we thought this worked really well in this particular situation. Use of wrap and concrete mixtures is feasible. You take a hit on strength, but overall the mechanical and durability properties show that it meets the minimum specifications. It should work well as a concrete pavement. And then the issues we had, primarily one of our conclusions why we think that this is one of the reasons why our concrete in particular was taking hits on strength. And this is also consistent with what Illinois found. They had some big conglomerations of asphalt and fine aggregates that were counting as coarse aggregates. And the moisture content correction, how you account for that is, the way we accounted for it was by slump adjusting our concrete. And from here on out, if this is going to be used more, we have to come up with a better process for doing that. And so our follow-on research that we're doing is, again, trying to decrease the cement content in these mixes and trying to come up with a better moisture content correction method. So with that, that's all I had. You bet.